Hello, big boys and girls, parents and grandparents, and everyone interested in AI and robotics. I'm Anastassia, and I am bringing to your attention AI Snacks with Romy and Roby, a podcast for technology muggles, not wizards. My show translates AI and robotic technologies from difficult to easier to understand. My show is a byproduct of Romy and Roby book series, which I write for children from 7 to 15 years old. I don't believe one can force knowledge on people, so I try to educate children and their parents about AI and robotics in the most entertaining and funny way. Why am I doing so? I am convinced that AI is changing the world around us, and we all must know about AI and robotics. So all my nice stories about Romy, a cat, and Roby, a little android, are rooted in science. And I write the science behind section for the book and my blog. And I go deeper into the realm of technologies in the science behind. So my podcast is a part of this section. And it's well suited for educators and for everyone who does not have any technology background. And now, we are diving into today's episode. I'm going to discuss today sensors in robots. And after today's episode, you will be capable to talk about how sensors evolved in the past decade, why are they important in robotics, what type of disciplines are involved into development of sensors and research and development of sensoric technologies, and you will be capable to tell what are the challenges in developing sensors today. And now let me open the studio to my wonderful guest. And now it's time to bring my wonderful guest to the podcast. This is a roboticist and AI scientist, Zubin Jacob. And Zubin, welcome to my show. And please introduce yourself properly. Tell us, what do you do now? And could you please walk us through your path, emphasizing a couple of moments which led you to where you are today?
Great. All right. So thank you so much, Anastassia, for having me on this podcast. It's such a pleasure to be here, and I'm looking forward to our conversation today. So just a little bit about me. My name is Zubin Jacob. I am a professor of electrical and computer engineering at Purdue University. So we are in Indiana. It's a couple of hours away from Chicago, if you know the Midwest of the United States. And my path towards doing, say, AI research or maybe robotics research is very unconventional and rather winding. In fact, I would say that my main area of interest is really photonics.
Yes.
That is really about how light can be captured, how do lasers work? How does optical communication work? So it's really, that is my core area of research. But it turns out, as we were working on these areas related to really light radiation or electromagnetic waves in some sense, we realized that, there's a lot of capabilities that AI algorithms and AI hardware brings to the problem that can really accelerate our research.
Yes.
And maybe even have new technologies and applications that were not really considered before. So the winding path, if I were to just summarize it in short, is really I'm a photonics researcher. And over the last 4 or 5 years, I have realized that these ideas really can go to the next level when you bring in AI, machine learning, and very unique hardware on these problems.
And it's just absolutely fascinating. And, when you talked about it, I was thinking about cognition and non-human cognition. So let's say if we look into the animal kingdom, obviously how some animals perceive the world has nothing to do how we perceive the world. So obviously we have eyes, we can grasp a certain part of a spectrum, but creatures which are different from us can see more, or they can see less, but then they have other sensors and haptics and obviously everything which is in the realm of acoustics. And so this photonic capabilities, you can equip myriads of machines and robots with those, and they would be probably across all kind of industries, right?
Yes. Yes. Excellent. So this is a really great question. And then maybe I'll give you kind of a context of how our research was also kind of inspired by some of the things that occurs in, let's say, the animal kingdom. So I'll start with the example of infrared radiation. So our eyes see kind of visible radiation. It turns out, snakes, when they are hunting for prey, in the night, they do have some sense of the infrared radiation and the heat coming from, say, a small mouse or a rat. And the snakes can actually sense that. And they can do it in the darkness as well. So there is already, like you mentioned, some sense of perception which, say, humans don't have that exists in the animal kingdom. Another really good example is that of the hammerhead shark. So if you know the hammerhead shark and you look at its head, it's really a little odd. It really does look like a hammer.
Yes.
Now, what scientists figured out, and that's not like very old research, that's just in the last 10 years. I mean, it was sometime 2013 that the research paper came out, and there was like excellent research showing that, the evolution preferred this hammerhead shark to have a larger distance between its two eyes on the two ends of the hammer, so as to speak, so that it can actually triangulate the prey really well. Because we require these eyes on the front of our, body to be able to triangulate prey. Now, the hammerhead shark, because its hammerhead, its eyes are further apart. And that makes it triangulate better. And in fact, it can see behind as well. Triangulate even behind it. So the special perception and senses that you mentioned absolutely is very vivid and very different in the animal kingdom. And it does call for inspiration for us to bring it to the robotics of the next generation.
Well, that's, completely fascinated. I remember working at Qualcomm, so I was the head of Europe for a couple of years, and I remember the engineers were constructing the eye of a wasp, and that was tremendously difficult because, it has nothing to do with how a human eye is built from the anatomical perspective. It was tremendously difficult, and what this was perceived and how it can capture everything and orient itself. It was mind-blowing and very, very difficult. And apropos sharks, it's really, yesterday I was recording a little video to explain kids and parents who aren't in technology the Bayesian methods. And actually...
Maybe I should sit in on these as well.
No, but, apropos sharks, so I learned, it was a coincidence that people found out there are sharks that are 420, 450 years old. That was unbelievable, and they used Bayesian networks to actually calculate it, and I was like completely mesmerized by what is going on in research and how statistics and modern AI influence actually everything around us. But it was a little segue.
Wonderful. No, this is great. Because since you were at Qualcomm, and these Bayesian methods are also used for estimation on networks and other things. So this is a completely new application of these ideas. Absolutely. No, this is fascinating. I should look it up.
That's really interesting. I am quite curious. So obviously, photonic is one aspect, and you are integrating the technology into sensors. Yes. And I'm just wondering, from when you've just started in science and where you've just been a student yourself to now, what changed in the evolution of sensors from there to what we see now? Could you talk a little bit about it?
Sure thing. I think I have to say that all our lives have been touched by this kind of sensor developments, right? The simplest example is, I don't know if you remember, there was a time when we did have to carry these big cameras with us,
yes.
right? And the thing is that some of the sensors were very advanced, and the lenses that surround the cameras, that's not the sensor itself, they are still a little big.
Yeah.
But the sensor itself has come such a long way that some of those megapixel cameras that we had, and those were high-end standalone cameras. I mean, our cell phones today can take images of the same stunning quality, right? So the sensor development has touched all our lives without doubt. And the scaling of the number of pixels, which really tells you how fine is the resolution of your image, that has kept on increasing. So it's clearly we've seen one huge advance of just the form factor, the power taken to really run such a sensor array improve. The other thing is just the cost.
Yeah.
I mean, we don't have to pay a huge amount of money to just get the sensors. And you can have these sensors on every car now, right? We have webcams, which are excellent, and they are really affordable. So I have to say that the cost is another big factor that has helped the technology to be very prevalent. And then I'd say the third thing, which I think is equally important, is that the compute power has kept on increasing over the last 10 years. So as to say that some of the algorithms that are used for changing the blur or improving the sharpness, or the color contrast, or being able to take images in low light scenarios, many of these algorithms require a lot of compute power, but our cell phones and are essentially the advanced computers that we had with us, say, 10 years back, sitting on our desktop.
Yeah.
So I would say that cost is a major factor, the scaling of the number of pixels, the form factor, and definitely the compute power that allows us to do lots more processing on our kind of handheld devices, or maybe on the robot itself. A lot of the processing is really coming to the edge, and I think that's those are many of the changes that we are seeing in sensor technology.
So for my audience, if we talk about the edge devices, we are really talking about the device like a smartphone on a sensor. So it means that the processing is on this device and not in the cloud. And this is a huge difference, of course, comparing to pulling everything into a huge data center somewhere far away. So, and I'm wondering, so those are huge benefits and huge progress of the past 10 years. But what are the largest challenges in your eyes?
Right. So I would say that a lot of the progress that we have seen is really accelerated because there's a very big connection between, let's say, the sensor industry and the computing industry. And many of these things are really connected to modern day fabrication facilities. So this is kind of CMOS foundry. These are just places where you would manufacture and fabricate this similar type of sensor array, as well as, say, the chips that we use. So it's really part of the CMOS foundry. But because of how advanced the CMOS foundry is, it's also very specialized.
Yes.
What that means is, as soon as you want your sensors to do things slightly different from what exists today, it's a really major challenge. And one of the examples, connecting back to our kind of just a conversation a few minutes back, you want your sensors to be able to, say, sense acoustics very well, or you want them to be sensitive to infrared radiation. In those cases, the same materials that are used in the foundry, they are not sensitive. We have to look outside this confines, and we have to think out of the box. What are the mechanisms that we will use? And then it turns out that it's very challenging to do that in today's environment. And we have to think about how are we going to integrate the next generation of sensors, bring the cost down, form factor down. How are we going to do all that? And pretty much start competing with the existing sensors of today, but have new capabilities built in.
Yeah, of course. I mean, the technology stack must be standardized somehow. And then it's quite a question how to bring the specialization into what the customer might need or what the research center might need. And in this context, could you please talk about the HADAR sensor and how did you create it? What was the initial impulse, the whole story? So obviously my Roby is imaginary. So the Roby, the android in the book, he's equipped with it.
Right.
This is great. He can do a bunch of stuff,
Wonderful.
right? He's a humanoid, a robot. I don't know whether HADAR might be integrated one day into humanoids. I don't know, but for sure it could be integrated into all kind of machines for healthcare, agriculture. Please talk a little bit about it.
Sure thing. So, I'm definitely, when you sent me the email, I was definitely fascinated by your character, Roby, and we hope that we will be on the pathway to bring in humanoid robots with HADAR equipped, right? And so this is great. And I look forward to learning more about Roby in the near future. So let me tell you a little bit about how we came about this concept of HADAR and what are some of the kind of challenges we overcame to really get to that point. So HADAR, just for your broad audience, I'll let them know, it stands for Heat Assisted Detection and Ranging. And that's an acronym. It's very similar in spirit to radar or LiDAR that your audience may have kind of heard about, or sonar, which uses, say, acoustic waves.
Yes.
And as we know, radar uses like low frequency electromagnetic waves for detection and ranging. Now, one thing which is very important is that all objects in nature, like you, me, the computer, these books behind me, they're all emitting thermal radiation.
Yes.
So it's just heat waves that are emanating from all these objects, and it's always present everywhere. And these, it's really in the form of certain radiation that our eyes cannot see, and it's in a different size of the spectrum.
Yeah.
Different kind of range of the spectrum. And the HADAR is really trying to exploit that part of the spectrum to give you detection and ranging information.
Cool.
And the crucial insight is that once these sensors work and once these algorithms work, it turns out that HADAR gives stunning images which are as rich in information as images in the daytime, even though HADAR is working at night. So this day and night equivalence is one of those big things that HADAR allows us to do. So that's kind of a broad picture. So now I'll tell you a little bit about how we got there. And so we knew about thermal sensors. In fact, these are used, I would say, maybe in the defense industry. It's used in the surveillance industry. So there are these thermal sensors that exist. What they do is that you can take a picture of your surroundings, and instead of the sunlight, which is normally what you capture with your camera, it actually captures these thermal waves that are coming from the objects. So that's a special type of camera, and they exist. But what happens is that these thermal cameras, if you look at the image, the resolution, the clarity, the information content is very different than what you would see if you took a cell phone image, right? So it's a very vast difference in contrast resolution. And if you think from the point of view of human beings, we have so much kind of evolutionary insight that when we look at a scene, we kind of know, we know what, there's a person. We know that. And we know, oh, that's a car. It doesn't look like a car in the day, but in the night, it does look like a car. Yeah. So we do use a lot of our perceptive abilities to reason, even in thermal images. Now, it turns out, if you had to give the same type of knowledge to a humanoid robot, it would actually fail a lot because it just doesn't see the connection between the daytime and the nighttime. Yeah. The nighttime is just very low resolution, low blurring. So the detection and ranging accuracies are even 100 times lower if you equip with a conventional thermal camera. So what we did was we came up with modifications to the thermal camera so as to be able to collect some colors, which are invisible colors, and also come up with some AI algorithms that allow you to see images in the darkness with the same resolution and clarity as, say, daytime images.
Yeah.
And that's what HADAR really stands for. And we came about it through a mishmash and sometimes fortuitous, sometimes circuitous route of sensors, algorithms, and then bringing them all of that together.
So this is wonderful. This is actually when software and hardware are cross-influencing and cross-populating in research. This is wonderful. Yes. You know, I was just wondering, because if we use such a sensor, it makes a lot of sense to have real-time stream of data, right? Yes. And I am just kind of thinking this might be challenging to capture it. And how do you clean it? How do you decide whether you have some biases in it? And of course, a pixel is a pixel, but I wonder whether, let's say, normal algorithms like YOLO work just fine with that, or whether you require something specialized just to work with this type of data.
Okay. That's a really good question. And that's definitely one of the challenges that is really part of current research, is that much of the kind of decision-making abilities of robots that really rely on, say, image stream coming in, video data, that requires very fast processing. And definitely right now we are in the research phase where the processing is very slow. So we have to spend maybe the next 3 to 5 years on working on the algorithms, the sensors, maybe even get the sensors to reject some unwanted data so as, improve the processing on board. And so the sensors need to get more intelligent than the ones that they have today. So building in some compute power in the sensor itself. So there are many of these directions that we are going in, and that's the way we kind of expect to overcome the challenge. Now, in terms of, say, state-of-the-art algorithms like YOLO, which allow you to, say, do some segmentation and be able to do, say, decision-making in autonomous navigation. Those type of algorithms are compatible with our HADAR approach. That's one of the reasons that we actually map our HADAR images to the type of images that really come from sunlight. Yeah. And we're able to do this from a physics-based mapping. And that really allows us to get a lot of compatibility with the state-of-the-art algorithms. Now, it turns out the way to avoid these biases, which are very difficult, is really using those invisible colors in the thermal radiation, using these sensor filters and sensor modifications. It allows us to collect more information about each object and each foreground, background, that allows us to some extent, overcome the biases.
Yeah. And I guess this is quite costly, the whole procedure, because just when I talk to companies about just, AI and AI research, I say, look, building an AI application isn't a piece of cake. Of course, if you have, let's say, the prepared model, fine. But if you do everything from scratch, just the amount you have to spend on compute, which you do not own, this is mind-blowing. I had seen numbers by Andreessen Horowitz that AI companies, which are not obviously those owning compute like Google or Amazon, they spend 25% of the revenue base on cloud.
Oh, okay.
And it seems like, from what I've seen in my practical life, it seems about right. So how do you cope as a research facility? So you are not obviously Meta or Amazon. So how do you do it?
Right. No, this is a really good question. And I think this number of 25% that you mentioned, I definitely did not know that. And it's definitely a big amount of resources that are spent on compute alone, right? Yeah. So, one of the ways that we are approaching this problem in general is really baking in a lot of the physics and the underlying layers of the model. So we really reduce, in some sense, you can think of this as it's a very, very high dimensional problem, but the laws of physics, the laws of thermal radiation are fixed. They don't change between day and night or different parts of the world. That really doesn't change. It's just the specifics of the scene changes, but the underlying laws governing them are all similar. Right. So this high dimensional problem, even though the data is high dimensional, does live on a physics based manifold, which you can reduce by baking in the laws of physics in your AI pipeline.
Wow.
So that's one of the things that we are actively exploring, is to make sure that our vision algorithms, our detection algorithms, they are all aware of the fact that, this is the spectrum of heat radiation. These are the laws given by, say, Kirchhoff's laws of emission and absorption of thermal radiation, which has to be true in all the scenes. And we are trying to mitigate some of the compute and data needed to achieve a given desired performance. And there's definitely quite some ways to go, but the initial results are very promising.
That's interesting. And what is your vision for the practical use of HADAR in different industries?
Right. This is a very good question. So I'll tell you a little bit about the challenges that we have, and then tell you, if we overcome that, what are the type of industries that we will affect. So as I mentioned, the one challenge is definitely like the real-time processing. Yeah. Second challenge is bringing down the form factor of the sensor and the computer. Right now, it's kind of big. So we really need to bring it down. And then, of course, is the cost and how widely can we deploy it. So these are some of the roadblocks that we have to overcome. But I definitely feel that the first place where HADAR would be used is definitely in robotics.
Yeah.
Once we get these things overcome, I can clearly see that there would be a sensor, which is our existing red, green, blue RGB CMOS sensor, but right next to it would be our HADAR sensor with HADAR processing. And you would have these two streams of data.
Yes.
And these two streams would be kind of overlaid for the robot or something to be able to take decisions, for example, that a human cannot take. And it could even be on an industry shop floor, or it could be, for example, in the mining industry, where you have, say, autonomous navigation in off-road environments in the nighttime. You want to be mining 24/7.
Yes.
So the nighttime definitely poses challenges, and being able to have these automated agents which have these two streams of data and are able to take decisions very quickly, clearly that is of a lot of industrial interest. So I think that's where I see the initial push. But as we go ahead, and if we can bring the cost down, then definitely agriculture is another big avenue. But definitely the cost to entry is quite a bit over there. The barrier to entry and that cost is an important factor to consider. And I think eventually healthcare, we would be very happy to look at healthcare. Surveillance, kind of thermal imaging is already used today in surveillance to a large extent. We have to think, what is the new kind of value addition that HADAR brings to the thermal imaging problem? But eventually I see the potential is that almost every single place where thermal imaging is used today, HADAR would have a role to play.
And what about your ecosystem? So, of course, you have your university and your students and your colleagues, and it's very interdisciplinary when you talk about AI and physics all combined. But who are other players and stakeholders interested in that? And how do you collect your information, where you get your inspiration? So could you please talk a little bit about it?
Sure thing. As a university professor, we definitely work closely with the government. Mm-hmm. It's just part of how the infrastructure exists, of research, the equipment, the data. And I should add that almost all the research that we have done so far, it's all open access. It's all in the public domain, and this is all funded by the government. And so we have our government stakeholders, and we do work with these funding agencies in the US. So, and they of course have a rather large database of knowledge, as well as expertise that they've gathered over decades that have benefited us quite a lot. So they have been excellent partners so far. And we also have connections with startups. So we are building kind of some technologies that we hope will be licensed by the startups. And at the same time, my students are very adventurous. So I have a really good team of absolutely stellar researchers. And some of them do have the entrepreneurial mindset and they do want to go on this adventure to try to see how do we bring this to market. There's one thing to really do laboratory research.
Yeah.
And show proof of concept experiments, but the other is really getting it in the hands of the consumer and the consumer being very happy with a product or a service. So we are definitely have some students who are really going down that path, and I'm encouraging them and helping them in whatever capacity I can to do that. So I'd say that's where the ecosystem is. And in the future, maybe the next time we chat, I'm hoping that I would have some good news to share about the startup and how it's going and so forth.
Oh, that's fantastic. And by the way, if you need some links to the European ecosystem, just give me a call because obviously I sit in Europe.
Yeah. No, thank you so much for that, Anastassia.
Yeah. And I mean, you're giving really wonderful context and content here. And I would love to bring you back on this very podcast. But I would like now to ask you a last question for this program. And what would you advise young people who would love to study AI and robotics? So what would be your advice?
Great. All right. So, I guess this advice is kind of similar to kind of the advice that I would give myself, because I even consider myself as, in terms of research, still a young researcher in AI, because we just started in this topic very recently.
Yeah.
So I think, and one of the things that I found very helpful was really focusing a bit on the fundamentals.
Yes.
And learning from the ground up. Because I think right now there is a lot of push to just start applications very quickly.
Yeah.
Right. And when you are young, that's the best time to develop fundamentals that can really be with you for a lifetime.
Yeah.
It's really tough to learn all these things because you just get so busy along the way. There are 100 different things. You're pulled in different directions. So learning those fundamentals when you're older is definitely more difficult, just because of the amount of time you can have a focused, deep work on certain aspects. So for the young minds, I would recommend kind of spending a little bit of time on the fundamentals before they jump into applications and so forth. And I definitely recommend everybody to be coding. Nowadays, maybe we can't get the compute that, say, Meta or Google has, but there's still so many avenues of getting free compute and running algorithms on the cloud that is possible today. And there's data available. There's a lot of help available. The new AI chatbots are so good at helping with coding that it's important to use the whatever help we can get to become better. So I would say focus on fundamentals, and also definitely code and implement things using all the free resources that exist today.
I mean, this is a fabulous advice, and this is really music into my ears because, sometimes we kind of forget that certain things which we are at all today, they existed already in 1969. The notion, for example, about the distribution shift in deep learning, how difficult it is to generalize for those models. They don't understand the way we do. It was known in the 70s. Right.
Okay.
And out of sudden we are kind of, those models hallucinate. How come? Of course they do. Because this is the very mathematics, so the fundamental of what is in them, right? And
completely.
It's just, I think it's worthwhile to spend time and talk to general public about those things, because it's demystifies the technology, and actually it saves money because you can see through some, I would say, fake promises some consultants or companies try to make. And as for coding, this is another music to my ears, because I'm saying, look, it will be as ubiquitous as, let's say, basic math. And I'm saying that probably I compare it with kitchen. Not everyone will be a huge chef, but everyone can fry an egg.
Right. Exactly. That's a great analogy. Yeah.
Yeah. So, Zubin, that was absolutely fabulous. Thank you so much. So Roby is carrying your HADAR. He is a friend with the cat Romy, who probably has a biological HADAR because he's a cat.
Okay. Yes.
But we will see what will happen to them because I plan quite a bit with those two. They will even explore the universe in one book, and maybe there would be some interesting HADAR applications for space exploration.
Excellent.
But thank you so much, and I wish you best of luck. Great funding for all your programs, the most talented students, and just have fun. And thank you so much for responding to my really note on LinkedIn. I did not know you before, I connected.
Wonderful. No, this has been an absolute pleasure. I mean, such a nice conversation, and good luck with all your endeavors as well. And I look forward to reading about Roby and Romy.
Thank you. And now, dear audience, it's time to bring Susan Ford to the studio with another reading from Roby, and the Secrets of Sleep. Thank you.
HADAR. This is the place in the book where the family goes on a working holiday. They travel to Jersey in the Channel Islands to visit the lab of Dr. Green, the CEO of Q-Bidder. Roby wants a hardware upgrade to help his family with more tasks. He would really like a quantum processor. During the journey, the family discovers that Roby is equipped to see in the dark. How does he do it? Dad stopped the car on the side of the road, overlooking a valley. Sunshine came through the clouds, shining randomly on scattered groves of trees and small groups of grazing cows and sheep. In some places, glimpses of moving bicycles could be seen. Further away, a single mower drew straight lines across a meadow. "We are so lucky to live in such a beautiful place," said Mum. "I wonder how Roby perceives beauty, as he converts everything into a matrix of numbers." "Thankfully, I got 3D cameras integrated into my hardware," explained Roby. "Besides, I am equipped with a so-called HADAR system, patented at Purdue University, allowing me to see in the dark. HADAR combines thermal physics and infrared imaging. My software makes me aware about anything around, thanks to this technology." "How does it work?" asked Dad. "Objects and their environment constantly emit and scatter thermal radiation. This creates texture-free images, famously known as the ghosting effect. For example, thermal pictures of a person's face show only contours and some temperature contrast. There are no distinct features. That is why it is compared to a ghost. HADAR recovers the texture from the heat signal and translates the temperature and texture into objects and entire scenes. Unlike you or any other human being, I can see in the dark, as if it were day." "How do you use numbers to make sense of what you see?" Dad persisted. "My networks operate with so-called matrices of numbers, which is just another way to represent a picture. I don't have biological eyes like you. I use these matrices and perform mathematical operations called convolutions to find features of the images, such as edges. Edges are elements in the image matrix that differ greatly in the value from their neighbours. Once I mathematically determine where the things in the image are, I use another model to classify them. In human language, I see. In my interpretation, I determine exactly what is in front of me. I didn't understand a thing about what you've just said," admitted Romy, chewing a piece of chicken. "But I can see perfectly in the dark without convolutions or any other scariness. Cats' large corneas and pupils, which are about 50% larger than humans, allow more light into their eyes. This extra light helps them to see more in the dark," said Dad. "However, I'm not aware whether animal anatomy and physiology research plays any role in building robots. At my institute, we studied how insects, like honeybees, or birds like pigeons, interact, and then we tried to blend little machines, a bit like flying drones, into the groups of birds or bees. As you know, our dean was very keen for Roby to stay in our family, as we've got Romy interacting with him all the time. Humans want robots and drones realistic enough that animals respond to them, as if they were their own flesh and blood, not just wires and plastic," explained Mum. "In Japan, they use little drones to pollinate flowers, as there are not enough bees left to do the job." The meal finished, the family got back into the car, and Mum took over the driving.
The reading from Romy, Roby and the Secrets of Sleep concluded this very episode of my podcast. Before we meet again in a week, please consider visiting my website, www.romyandroby.ai. Please consider pre-ordering Romy and Roby and the Secrets of Sleep, which is the first book of the series and dedicated to quantum computing. But until then, goodbye, and let's make AI technology safe and beneficial for all of us. Thank you.